Now bundle, why do we call it as a bundle, right? That comes from this. So for example, right, imagine that I have a camera here, then I have a camera here, maybe, right, I have something like that, right, whatever. Okay, or else let me just draw it a little better. So maybe, right, I go this way and then I go this way. Okay. Now I have a scene. Okay, some points are there. Okay, this is one point, this is one point. There are several such points, right, in the scene, whatever. Okay, now if you actually think about it, right, so here are the, say, centers of my camera, right, which is what is the pose that I've got from my whatever method I apply. I have some, say, initial estimate, but those estimates I know, right, are not really exact, right. I know that probably there is some error and all of that. But if you really think about it, right, what will happen is, see, for example, I mean, if you kind of, right, look at this point, right, I mean, it's going to come and probably hit here. The other point will come like that. I mean, third point, right, will come like that, and all this, right, I'm assuming that you have an image plane, right, which can actually, over which this will fall, and then maybe, right, beyond a point, you may not even be able to see these points. For example, this camera may not see this and that, it may not see. Okay, but then the next guy, right, perhaps, right, will see this. Okay, and then it can see this. Then maybe, right, it will also see this, whatever, right, and then maybe, right, it won't see this. Maybe it will see this, but then not the other 2 points, and so on, right. So you can understand, right. So what is happening is, so you have your 3D scene, right, and there are these. So all these are your scene points, right, and you have these rays coming out of the scene points, and then each one is going and hitting the image plane of whatever camera is, let's say, right, within its view. Now, if you look at the image plane of any camera, right, now you see that a bundle of rays are coming and impinging on it, right, depending upon the say, number of scene points, right, which you have. And of course, you have a whole image, right. It's not simply these points from where the rays are coming. There is everything out there. But then we know that we have only the correspondences for these points that we have shown there. Only for them we have the correspondences. And what we are saying is kind of, and then right, this is the pose. So we have like C1, C2, C3, C4. We may just want to fix the coordinate system with respect to C1, and then think about everything else as like some R, T, right, that we need to find out. And we have some say, initial estimates, right, for the poses, and we have some initial estimates for the XYZ also. But we are saying that, right, that by itself may not be exact because of the feature correspondence errors and also. So ideally, if you look at it, what should you be doing, right? If you look at this bundle of rays that's coming in, so bundle adjustment means that you want to adjust these rays. What does it mean? Adjust these rays, right? In the sense that these 3D points themselves may have to move around a little bit. It need not stay where you have given as the initial estimate. The even 3D points may have to move around the place, right, where they are. They may have to move around a little bit, and at the same time, what should also happen is perhaps the camera poses, right, should also probably move a little bit because they may not be exact, right. So the centers of the camera could also be moving around a little bit. You may have to move them around such that when you actually project, right, the reprojection error, as it is called, right, I mean, I have not used that word till now, but reprojection error is something like I have a point correspondence for that particular, say, 3D point. Let's say for this 3D point, right, I know that right, that my correspondence is here, but then when this point moves during my optimization, right, when this point moves, and then when I join it with the optical center, right, it may hit somewhere close by. Right, it does not have to hit there because I do not know whether that itself is correct. So when it in this kind of optimization, when this ray comes and hits, now the reprojection error, you want that to be as small as possible, right, because you can only go by what you have, and you have these say, correspondences with you. So if you look at the correspondences, right, now the way to see the correspondence is fix a scene point, and that scene point, right, you kind of pass it through one of the optical centers, we get 1 point, pass it through the other optical center, you will get another point on the image plane, right, which is a projection that you are doing. And if you have point correspondences, you know where these should come, right. I mean, you know the correspondences with you, you are kind of doing this bundle adjustment, and you are trying to see how should I get this reprojection error to be as small as possible, right. That's the idea. I mean, is that clear? Of course, it's a kind of it's more a kind of a statistical kind of framework, which I will tell now. But the point is, this is the idea, right? Everything else, the math and all is okay, right? We can kind of say figure that out. But I want this to sink in. When you say bundle adjustment, right, this is exactly what you mean. Okay. Now I'm not going to write all this, okay, because I think I've already said. Okay. So the idea is this, right? So what you want to do is, so you want to account for noise okay, account for noise in the feature correspondences. And some of them could be say outright wrong. I mean, it's not just a small amount of noise. Some of them could be outright wrong, in the sense that you are saying that this point is that, and then that could be actually wrong. It could be outright wrong. And you see, until now, right, what we have seen, we have only used what are called linear approaches. We have only used linear approaches, right? I mean, we have always been going to say SVD and, right, I mean, solving everything, used linear approaches. But then if you want to account for such things, right, where you have to account for noise and right, I mean, noise in the feature correspondence, because finally the only information that you have are these feature correspondences, right? Let's be clear about it. There is no other information that we have. Whatever you derived is also based upon that, and whatever you are going to derive will also be based on that, right? Nothing else we have. So all that we know is, right, from that point, right, 3D point, if I come, right, plot a ray which actually, right, intersects the center, wherever it intersects, that's where my actual sort of, right, point should be. Whether my sort of feature correspondence occurs there or not, we do not know. That's what this is trying to do. So we have used only, right, linear approaches, and now it's time to sort of account for noise. And the moment you account for noise, right, what does it mean? So it means that right, if you kind of think about your x tilde, right, which we have written as p x tilde, right, plus some, let's say, n, right, because this noise, right, could actually come. Okay, so what we are saying is, right, there could be a noise, and the simplest thing to do is to assume that, right, this is actually AWGN. The other thing, right, that we have not also taken into account in the previous thing is that what if let's say if one point, right, you can't see in let's say in some other frame, right? I mean, when you're doing this, right, it's quite possible, like I showed in that particular figure, right, that some points may not even be seen by a certain camera. So what is called a visibility map, right? A visibility map you have to have, right, so that you know, like, which ones, when should you take that cost into account and when you should not. I mean, you don't even see that correspondence, there's no point trying to right, compute the error, right. So what one does is the following, right, and since we are assuming noise to be AWGN, right, so the thing to kind of look at it is look at what is called right, a map estimate, what is called a maximum a posteriori. So for example, right, I mean, what this means is that if you have some kind of a prior knowledge about, let's say, x. Now I'm going to write this in a sort of a simple form. Okay, suppose I say that, x, r, and then t, right. These are the only unknowns that I have. By x, right, what I mean is, I mean the scene points xj, the set of scene points xj, okay, j equal to whatever, what am I using here? Let me just be kind of consistent. So j is equal to 1 to n. Okay, that means I have that many scene points. Each is a vector, by the way. Okay, so this x is actually a collection of scene points which I have to find out. R is, of course, rotation, but again, right, R will have like so R will again be a set. So it's like Ri, right? I is equal to how many views you have. What am I using here? M. Okay, 1 to m, and similarly T, right, will actually, which consists of all these poses. Right, Ti I equal to 1 to m, right. All these are our unknowns, okay. And the idea is that, right, when you say that maximum a posteriori, right, what you mean is, after having observed, what have you observed? The feature correspondence, right, nothing else. Okay, so after having observed, so you want to say that, right, can I kind of maximize right, p x r t after having seen, right, x tilde. I mean, there could be a prior probability which we don't even know what it is, right. I mean, how they should occur together and all, we don't even know. So therefore, typically, right, they are simply used as a uniform, just as assumed to be uniform, because you don't have any specific knowledge about it. So simply assume it to be uniform, and therefore, right, what you want to do is maximize the kind of a posterior probability, which is like having seen x tilde, right. I mean, I want to kind of maximize the posterior, but then this we know is actually proportional to p of x tilde, right, given whatever x r t. By x r t, right, I mean the entire group of poses, the entire set of 3D points, right. This is not one pose or one camera pose, right. I mean the whole set, right, p of x tilde, right, and into whatever, right, P of x r t. Right. And since, right, this we don't have any knowledge about this, or we can simply use it to be uniform. Okay, then as you know, right, map and MLE become the same now. So now we are looking at something like a maximum likelihood estimation, right. So what does it mean? It means that, right, find that XRT combination which maximizes the likelihood of having seen x tilde. Correct. When x tilde is what you observe, and therefore it maximum likelihood is what? Find the unknown, whatever theta or the parameters that you have, such that it maximizes the likelihood of having seen the observations that I have seen. Right. So in this case, x tilde. So x tilde by x tilde again mean the entire set of feature correspondence, not one feature correspondence. Right. I am just using a notation like this, but I hope the information, right, is clear, that we are looking at the entire set of feature correspondences. Right. And right, if you have a model like this where, let's say, x tilde is actually related to XRT in this form, right, this P will contain your R and T, x tilde has your x, right, then what does it mean? So this is equivalent to maximizing, let's say, right, with respect to, of course, XRT. Okay, you want to maximize P of so what this means is n is equal to x tilde minus P x tilde given whatever XRT. Right, because we are assuming an additive Gaussian model for the noise, for the noise, right, and of course, once you give XRT, then n is known, right. I mean, there is no uncertainty here. Once I tell XRT, therefore this will be simply because you have assumed the noise to be Gaussian, right. So you can actually throw this out, right. You don't have a dependence on that anymore. So it is simply P of n equal to x tilde minus P x tilde, which is simply e raised to whatever, right. You will have some normalization and then e raised to power minus whatever norm of x tilde minus P x tilde square, right, and x tilde is actually 3 cross 1, that we know, right, all that we know. Okay. So now you see that maximizing this probability, right, I mean, is equal to, then one should just take the logarithm, so that, right, things become easy, and all of this boils down to actually maximizing that probability, right. The posterior is equal to minimize. So what you want is an arg max, right, with respect to what is this, XRT, and in this case it becomes arg min, right, because of the fact that noise is Gaussian. So it becomes arg min norm x tilde minus P x tilde square, right. This is what we want, and this encompasses, this has R and T in it, this has all your x's in it, x tilde. Right, all the see, right, 3D scene points are kind of sitting in this x tilde, and then P has R and T, and this is what you want to do. Right. So basically, effectively boils down to a problem like this, and this, right, typically we write this as a kind of a loss function. Okay, this whole thing, the usual form in which we will write this as, let's say, x tilde, or I can even write it as x. Okay, because you don't need that tilde really, right. You are only interested in x, R, T, again the entire group of poses. And because of the fact that, right, I have assumed m number of views, okay. So I goes from 1 to m, I have assumed n number of scene points, so j goes from 1 to n, and then there will be a variable, okay, this I will explain, okay, there will be a variable theta ij that will multiply this norm. I am going to write this as xij minus a projection pi is really a projection operator, which is a function of xj ri ti norm square. What does that mean? So right, what this actually effectively means is, now we are coming from, say earlier, right, we were trying to match the feature correspondences, right, directly. Now we are coming in an indirect way. So right, what we are saying is, if you fix a view, right, so if you actually, what to say, right, I mean, if you actually fix okay, j equal to 1 to n, right. So to kind of, right, think of, okay, xij is, okay, let me just write this down, is the jth feature point, okay. So this is the xij is the jth feature point in the ith view. Ith view means ith image, okay, in the ith view, right. So what you are saying, it's like this, right. So you have, so see, jth feature point means that particular 3D, the corresponding 3D point, right, whose image coordinate is xij, that is what we mean. Okay, so you have some coordinate like say xj, and then what you are saying is this has a correspondence, sort of, in the sense that we know that xj maps to some, okay, in the ith view. Let's say in the first view, right, this is some x1, what is it, I mean, so if you call this as, yeah, ith view, I is 1, right, so I'll call this as x1j. Then when I okay, now the way I've drawn it is not very correct, okay, but I mean, like, I should be drawing it like this. So this is my x1j, and then let's say, right, I mean, I have something like this, right, here is where my other center is, the camera center. Then this is my second view, right, so this is like x2j, right. So as my view changes, and I know that, for example, I know that this point, right, there is a correspondence which I got from SIFT or SURF or something, but when I kind of do this bundle adjustment, this xj can actually move around, and when it moves around, this point can shift, but I have the observation which is my x tilde, right. So this is my observed point which is coming from some SURF or SIFT, and this is a projection. Okay, this guy is this guy. This is like xij j dash or something, if you want to call it, and this is called the reprojection error, right. This term is actually the reprojection error. This is clear. It's the same kind of thing, right, whatever we saw earlier, except that, right, and all of this we need to do for every kind of 3D scene point. So if you fix a 3D scene point, you can say that a correspondence that I ought to get for this across the images should match as closely as possible to a projection of this point onto, let's say, every camera center, onto the image plane, right. And then I change my scene point, I go to the next scene point, I do the same thing. For that, again, right, I have a bunch of feature correspondences. I'll have a projection that I will do. I will say that, right, make this as small as possible, right. That's all you are doing. Okay, and then this theta ij is actually a visibility. Right. What this means is that if you do not have a correspondence, okay, then you are sort of assuming that probably that is not actually visible. It could also be that your SIFT did not return it for some reason, whatever it could be, right. But we simply assume that right, in this summation, right, now when we are doing from I equal to 1 to m. So in a particular view, if you don't have a correspondence, then we will assume that theta ij should be just 0 there. I mean, we should not take this sum there into account because we don't have a correspondence. Okay, so this theta ij is 0, or let's say theta ij is 1 if the jth point is actually visible in the ith view, Jth point means that is the 3D scene point. If it is visible, else it is 0. All that it means is in the summation, right, that term you won't include, you will sort of throw it away and then do the summation over the rest. Okay. Now there is a simplification of this, right, which you can do. So for example, right, I mean, so this entire operation is what? This is nothing but px tilde, right? That's what this is. No, this is projection. So if you write your p as involving everything, your intrinsics, everything, right. So if you write it, I mean, you will have like P11 to whatever PM14 and then P31 to P34, right. This is what you have as actually a 3×4 matrix, right. This is what your P. So if you do P into x tilde, right, that will give you a 3×1 vector, right. And suppose you call the first scalar value, right. Suppose you call this as what is that notation? Pij. Okay, so suppose you call this as Pij. Okay, this is small p, by the way. Okay, this is Qij, and this is lambda ij. Okay, what this means is that Pij is but the first row or first element. In fact, I mean, there's no like a row. There's only one value. First row of px tilde. This is the second row of px tilde. Row means there is only one value, right. It is a vector 4×1 multiplying 1×4 multiplying a 4×, just a value, right. Whatever is that value, that is Pij, and therefore, right, what you can do is you can replace this guy and I mean, instead of having 3 elements in Xij, you can actually reduce it to 2. And what you can do is you can write this L. So the simplified form, right, will look like this: XLRT is equal to again the summation over I and j, and then theta ij will remain, and then inside, right, you can write this as Xij. Now right, that is a vector. Now I've now brought it down to a scalar now, okay, and Pij by lambda ij square plus yij minus qij. This is all you know now, right? Lambda ij the square. I mean that's your third element. No, you have to scale the first and second by the third, right, to get the actual coordinate. So the actual image coordinate is xij, yij, right? That is the actual image coordinate, and therefore, right, this can be further simplified, okay, into a form like that. And theta ij, all that is the same, right? And this is what is now fed to actually. This you can solve in different ways, but then the most used algorithm is what is due to is actually a nonlinear least squares method. It's already there. It's not built for this structure from motion at all. It's called Levenberg-Marquardt. I think I've got the spelling correct. Levenberg-Marquardt method of nonlinear least squares. Okay, and this is actually a non-convex optimization. Okay, so this is a nonlinear least squares method, which is available in MATLAB and all of that. Right. I mean, there was a time when I used to actually teach this, but it's not needed. Okay, people simply use this now. Okay, I mean even bundler and all just comes as a package now. Just throw your thing inside, it will just run it for you. Okay, so this Levenberg-Marquardt is what you have to use to solve this.